Hey everyone, welcome to the next video of section 7.9. So this video isn't really specifically section 7.9, it's kind of like just a wrap up for chapter 7 overall. And I'm going to talk a little bit in this one about higher dimensional systems. So we spent most of the time focusing on 2D systems or 2x2 matrices just because those are easiest to handle, easiest to solve. But a lot of stuff we've done also works for more functions in a bigger systems. So I'll spend a little bit of time talking about sort of what things work, what things don't, what things become a lot more complicated as you increase the number of functions. So let's just go ahead and just start talking about that. So for higher dimensional systems, we're going to still say we're looking to solve, say, the equation x prime equals a times x, and a might still be a constant coefficient matrix just to make things easier. Now, a lot of the stuff still works the same way. So you still look for solutions of the form c times e to the rt, where c is an eigenvector of a with eigenvalue r. So that still works the same way, right? That guy will still solve the problem if c is an eigenvector with eigenvalue r. And finding eigenvalues follows the same procedure, where you take your matrix, you subtract r off the main diagonal, and then you take the determinant. However, that last one there is a little more complicated, and the idea is the determinant. So determinant becomes much more difficult to calculate in higher dimensions. So for instance, to do the 2x2, you only had to do 2 different multiplications and subtract them. For a 3x3, there are 6 multiplications involved, and it goes up by factorial. So this goes like n factorial calculations for an n by n matrix. So once we get beyond 2 or 3, it just becomes impractical to try to solve it out by hand. You could, it would just take you forever and wouldn't really be worth the work you'd be doing to solve it. The other thing that happens is that with more dimensions, the ways the eigenvectors can get messed up when you have repeated eigenvalues get worse. So repeated eigenvalues can cause, I'll just go with saying worse results. So the idea was in the 2D case, right? Once you found an eigenvector, you had to go one more step to find a generalized eigenvector. And that was the end. That gave me 2, which is all I wanted. Well, what if I have 4 dimensions and that's not enough? I need another solution with that same eigenvalue. So then I have to go a step beyond the first generalized eigenvector to find a second generalized eigenvector. And it just stacks up on top of itself and it gets ridiculous very, very quickly. So you get worse and worse types of eigenvector sort of mess ups as you get to higher dimensions. So you may need more iterations of the eigenvector procedure, because you might need more than one generalized eigenvector. You might need 2 or 3 of them because there are more dimensions you have to hit. You also, say, may have 2 different eigenvectors, but still need more. For instance, if I have a triple root, this could be the case. If I have a triple root in the polynomial and I have 2 eigenvectors, well, that's not enough. I still need 3 to match having a triple root. So things just get more complicated and more complicated as they go on. So really the overall sort of guideline is calculation becomes more complicated, but the ideas are the same. And this is really where computers can be helpful. Why? Because you can set up the calculation to do because you know how that works. That's the same as it was for the simple system case. But the calculations become so difficult, so complicated that just throw it at a computer, have the computer do it for you, and then use what you get to interpret the results the computer spits back out at you. So for example, just to give you examples of what something looks like, if I have a matrix, if I have a 5x5 matrix, A, and it's 2, 0, 0, 0, 0, 0, 2, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 0, 3, 1, 0, 0, 0, 0, 3. So I wrote this out matrix in a very specific way because this is something that if you take linear algebra, you probably see matrices in this form. This is called the Jordan form of a matrix. Not important, don't worry about it. Then what I know is my characteristic polynomial is r minus 2 cubed, r minus 3 squared. And I will find 2 eigenvectors for r equals 2 and 1 eigenvector for r equals 3. which means I'll have to do the generalized eigenvector procedure on both 2 and 3 separately, and then put them together. So overall, I do all that. My general solution is going to look something like this. For that matrix, I'm going to get, so I get a C1, C1, and e to the 2t, because I'm going to find that vector. I'm going to get a C2 times like C2, e to the 2t, because I'm going to find a second vector. And then I'm going to get a C3 times a C3 t e to the 2t plus an eta 1 e to the 2t. So that's like my generalized eigenvector for that. Now I have like C3 there because I have both C1 and C2, so it's going to be some combination of them to give me that C3. And then plus a C4 times a zeta 1 e to the 3t, that comes from the eigenvector I find here, plus a C5 zeta 1 t e to the 3t plus eta 2 e to the 3t for the generalized eigenvector for that one. So it gets kind of nuts when you start doing this, and especially if you have to do like double iterations of this generalized eigenvector thing, it gets bigger and bigger and bigger and gets really nasty. So the point of this is saying that the higher order systems, all the stuff you've learned still works. It's just harder to work with the computations. The stuff gets a lot trickier. It's also harder to draw things. The point of the 2D also being really nice that we can draw these phase portraits, which are really easy to draw and show you what's happening to these systems instead of having you, have to visualize it because it's in 5-dimensional space. 2D you can draw it, and that's always nice too. All right, that's the point I want to make in this video, just talking a little bit about the higher order systems, the higher function system where you have more functions involved, and sort of what goes wrong, what still works. And the ideas are the same, but computations just become a pain to do correctly. All right, that's it for this one. Thanks a lot for watching, and I will see you in the next one.